The person walks at a constant rate. So the red guy is walking at a constant rate, and the tip of his shadow is also moving at a constant rate. So like this is moving at a constant rate here, and so is he. Now this, though, is moving faster than he is. But it's not speeding up. It's not getting faster and faster and faster. It's just moving quicker than he is. All right, the next example I don't have an animation for. This is a problem off of a test. So I figured I'd just grab it and throw it on here. Or we would do it today, just so you can see an example. Remember I told you last time that when I do exams, what I do is I give you several problems to choose from, and you do a few of them. That way, you know, if you just can't get the geometry right on one of them, it doesn't cost you a huge part of the test. Hopefully another problem with a different sort of geometry, you feel better about it, you know what I mean? Equation, given, want, all right, implicit. So this problem is a little bit different than all the problems we've done in the past because they're giving us some information about time, right? Like at 2 p.m. we have a certain situation, and then they're telling us how these ships are moving, right? And then they ask us what's happening at 5 p.m., so 3 hours later, right? So can you all read it? Yeah? Can you all see that? So at 2 p.m., ship A is 60 miles east of ship B. Ship A is sailing north at 15 miles per hour. Ship B is sailing south. Oh, this is north and south? Okay, yeah, that'll work. How fast is the distance between them increasing at 5 p.m.? All right? So I recommend for something like this, even though we're going to do a general and an instant picture, we're going to try to, I'm going to first just do some scratch work. I'm just going to draw like snapshots at the different points in time. All right, so let's just see what's happening at 2 p.m. So at 2 p.m., I have ship A, right there. And ship B, let's see, ship A is 60 miles east of ship B. Oh, I have this wrong. So maybe I should do it this way. Here's ship B, right? Ship A is here, right, east of ship B, and this distance is 60 miles, right? That's what's happening at 2 p.m., right? Now, at 5 p.m., what's going on? Well, ship A travels north, right, at 15 miles an hour. And then ship B travels south at 40 miles per hour. And it's 3 hours later, right? So if you think about where they started, I'm going to draw in blue where they started. Here was ship B, here was ship A, right? We know the distance between them was 60. That was happening at 2, but now we're at 5 p.m. So where is ship A? Tell me where ship A is up here. How far has it traveled? 45 miles, because 15 miles per hour for 3 hours, right? So this is now 45 miles, right? Yes? Ship B, the other one, has gone south. It's been traveling for 3 hours as well, and it's traveling a lot faster than ship A. It's traveling, what, 40 miles an hour? So this distance from here to here is what? 120 miles. It's not drawn to scale, okay? All right? At this particular instant time, that's 5 p.m., we want to know how fast the distance between them is increasing. So I'm going to draw a line connecting these from here to here. The question is, at exactly 5 p.m., how fast is this red line growing? You can almost think of it as like if one person was let's say we had this rope tied to this ship, and then you had a person holding the other rope on the other ship. The question is, how fast is that rope coming out of your hand, right? Rope burn, right? So we want to know how fast this is growing. Understand? This is just me kind of setting things up. Right, just in my mind, I'm drawing it, I'm just kind of getting an idea of what's happening. And now I'm ready to draw everything over here. So the instant is that picture I just drew at the end. Okay, I'm going to put that here. So here's where they started, right? Here's where they started. This is up here at 45, and then this is down here at 120. And I'm interested in this distance here to here. Could we figure out that? Do you think we could figure out how long this is? I think we probably could. I think we probably could. But for now, I'm just going to leave this, all right? Now, in general, yes?
Shouldn't you also write that it's 60 miles apart?
Yeah, we could put that here. This right here is 60. I thought it was, yeah, it's implied there, but yeah, we should put it there. Right, that's 60. That's not changing. Now, in the general picture, what I'm going to do is I'm going to kind of do what I did before. I'm going to have this imaginary little connection between these two ships. But now this right here is ship A. This right here is ship B. I'm not actually fixing where they are, right? And since it's arbitrary, I should probably assign variables to those, right? What do you want to call the distance from here to here? A. You want to call that A? I'm going to go little a. Is that okay? And then this one right here, B, yeah? So that's ship A's distance. That's ship B's distance, right? Okay. Should we draw this? We want to know that, right? We want to know how fast that's changing, so why don't I draw that in here? What do you want to call that?
Big H.
Big H? You want to call that big H? Okay. No problem with that. It's almost like a big hypotenuse, right? All right, and then also we could probably label this as 60. Just remember that, right? I think that's a pretty damn good picture so far, right? Any ideas on what we're given and what we want?
The change of A.
We're told how fast A is changing, right? That's the speed of ship A. What is the speed of ship A? 15. So I can write dA dt is 15, right? Miles per hour, whatever. You can put that here, mph if you want. All right. What else am I given?
Ship B speed.
Ship B's speed, dB dt. And that's what?
40 miles per hour.
40, right? 40 miles per hour. Now, last class I told you that we had a problem where the plane was flying and we had labeled the distance as x and the speed of the plane was whatever it was, I forget, 600 or something. And I said we had to make it negative because x was shrinking, right? In this problem, A is growing and B is growing. Even though they're in opposite directions, they're both growing, which means that these are both going to be positive numbers, all right? If ship B was moving north as well, right, we would still keep it positive. It's all about, well, if we drew the B like this way, it's all about whether or not that length is growing or shrinking in the picture, all right? What do we want?
Speed.
Okay, speed of h, right? We want to know how fast h is changing with respect to time. I will say this, when it comes to assigning variables, like we used little a, little b, big H, that's completely up to you. My advice is to stay away from ever labeling anything little d. Because when you look at a derivative, it would look like this, dd dt, which is just a little odd. To me, that's a little odd to be like dd dt. That's, if you want to use little d, use little d. I'm just saying I avoid it because I think it just looks weird. Okay. Hey, I think, oh wait, we're not done. We want to know this, right? Okay, we want to know this at what moment in time? At 5 p.m., right? At 5 p.m.
3 hours, right?
Or 3 hours later, right? There's a lot of things I could put here. At 5 p.m., 3 hours later. Or t equals 3, right? Or
45 miles later.
What is this?
A.
That's A, right? At the instant time, A is this and B is this, right? So I could say I want to know how fast h is changing with respect to time at the moment that a is 45 and b is 120. You see? There's so many different ways I could say it. I could talk about time, I could talk about a and b. I'm going to go with a and b because most likely the equation I'm going to come up with is going to have a in it, right? It's going to have b in it, and it's going to have h in it. All three variables have to be in this equation because when I differentiate it, I need all of these, right? So if I'm going to have a, b, and h in my equation, I probably want to know what's happening to a and b at that moment in time. All right, equation time, I think, right? I think we're pretty much set up. We need to connect these variables together, all of them. Connect them. Do some more scratch work here. This is the picture you have to work with right here. You have to get an equation, right? You can't fix anything yet. Don't tell me A is 45. Don't tell me B is 120. Don't look here. You're not allowed to. After we differentiate, you can look here again. From here. Connect A, B, and H all together. You got something?
Yeah, it's the diagram theorem, but it kind of looks weird, but you just need to change B to be on the side of A. So it looks like just one triangle.
Okay, so like if this distance right here is B, you could just move it over here like this,
Yeah.
right? That would be B as well, like from here to here. That would be B. And then go straight across. That's a right triangle now, right? Everyone see this right triangle? Do you know this side? 60, that's not changing, right? And so you have this side, and you have the hypotenuse is H, big H. We got it, right? Pythagorean. So my equation should be what? 60 squared plus this whole side, right? Squared. This whole side is A plus B. So I have to write A plus B squared equals the hypotenuse, which is capital H squared, right? There it is. That is an equation that connects little a, little b, and capital H together. How do you know to do this? I don't know. You just saw it, right? Okay, you saw it, you told me to do it, I agree. Now everyone sees that, right? You either saw it or you didn't. If you didn't, now you kind of know to start looking for something like that, right? Just want to mess with the geometry until you get some relationship. There might be some other relationships that we could have done, but I'm guessing they'd probably be a lot more complicated than this. This is pretty clean. Implicit time. Differentiate with respect to t. Okay, let's do it. I have a plus sign here. I can do these two separately, right? So what's derivative of 60 squared? 0, right? So don't tell me that's 2 times. This is a constant. 60 squared is a number, right? So derivative of that 0. I'm going to put it here. Okay, plus. Now, be real careful here. You're taking derivative of this, which is the derivative of something squared. Chain rule. So first thing that happens is 2 comes out, and then you have a plus b. Don't take derivative of a plus b yet, right? The 2 comes out, it's a plus b to the first power, right? That's what happens first. Then you go inside and take the derivative. And you do them separately because there's a plus. And that's being multiplied here, right? And there's going to be 2 terms when I do this differentiation, so I better put it in parentheses. What's the derivative of the first one? dA dt. Plus derivative of the second one? dB dt. Are we done with the differentiation now? On this, for this one? Yes, we're done, right? 2 came out, that to the first power, derivative of what was inside, got it, equals derivative of h squared. 2 capital H times dH dt. Chain rule. I don't want this 1 here. There we go. This is an equation now that connects everything together, right? in order to solve for, what are we solving for? Shit, I forgot. DHDT. Oh, that's nice. We're going to solve for this, right? We're going to get this, solve for that. So I'm happy I'm seeing that there. To do that, I need to know what A is. Do I know what A is? See, now I can go to the instant in time. I know what A is. I know what B is. Do I know DADT? Do I know DBDT? Do I know H? I can find it. I don't know it though, right? Like earlier we were talking, you know, maybe it would be useful if we found this, but I don't know if I'm going to need it. I'm going to need it. So where do I go to solve for it? Like how can I solve it? I can go back to this equation right here. This equation, I know what A and B are, so I should be able to solve for H. So I'm going to use that equation to get H. So I'm going to put that here. I need H. So I'm going to use that equation, 60 squared. Someone get a calculator out. A is 45, B is 120 squared equals H squared. So I need you to do 165 squared plus 60 squared, add those together, take the square root, and give me the decimal answer. I'm going to go with the decimal. It's fine. 175.57? Let's just say 6, approximately H. Anyone else get that? This squared plus 165 squared, add them, square root. At least one other person got it, yes or no? Yes? Yes? Okay. All right. Let's plug them all in and let's crank out this answer, all right? I told you this would be fun. All right, so here we go. We're doing this equation. We're plugging everything into this. All right, A is 45 plus B is 120, right? And we're multiplying that times dA dt, which was 15. I just erased it. Good job, Robert. Plus dB dt, which was 40. And then that's equal to 2 times H, but we just saw that H was 175.6, and then times dH dt. So this is the plug and chug step, right? We're just plugging everything in, cranking out an answer here. So please, somebody on their calculator, do 2 times 165 times 55 for me. My calculator's dead, or else I would, well, maybe it's not. It was acting real weird yesterday. It would come on, then would turn off. I think the batteries are 18150, right here?
Yes, sir.
18150. Any seconds on that?
Yes.
Yes, okay. On the right side, I'm going to just do 2 times this, 351.2, and then times dH dt, and then divide both sides, so 18150 divided by that answer. 51.7 approximately is dH dt. And this is measured how? Miles per hour, because H, right, is the distance between these ships. And we're measuring the distance in this problem in miles. So it's miles divided by the time, and time is being measured in hours here. So see, I don't carry the units through the whole problem. I just look at the very end. I think about what each of these is measured. You know, what's the unit for H? What's the unit for time? And then I just put a ratio, miles per hour, right? That's technically what MPH means, right? MPH really means miles over hours. 51.7 miles per hour. That's how fast the two ships are moving apart at 5 p.m., at exactly that moment. What if you did this problem and you got an answer of 60 miles per hour? What would you think if your answer was 60? How fast is ship A moving? 15 miles per hour. How fast is ship B moving? 40 miles an hour, right? They're 60 miles apart, right? Let me do it the other way. It was this way, right? So ship A, ship B, right? They're 60 miles apart. What if they were just like this? How fast are they moving apart? 55, right? That's the fastest they could ever move away from each other, is if they had been lined up and just started moving away. So if you got an answer of 60, you should be like, shit, something's wrong, right? Because if I move them apart, you should never get past 55 miles per hour, right? That's how fast. This right here, 55 miles per hour is the speed that they're moving away from each other. So I'm just trying to get you to see that the further they get away from each other, right, the closer this number should get to what? 55. Like at 5 p.m., they're already it's almost like they're lined up, right? Imagine what it would be like, 10 hours later. This should get closer and closer to 55, closer and closer and closer. And you could actually figure that out by replacing things in here and taking a limit and all that, but we're not going to do that, all right? All right, fun. Next problem, yes? There's no such thing as doing too many of these problems, all right? Ooh, the classic conical cup problem. Love this problem. Imagine computer programmers that have to render these 3D graphics for these video games, and how much they have to have the computer calculating related rates. How when one thing changes here, how that impacts the change somewhere else. Like, there's so much calculus in that. Now, we have the computer do the calculus. Like, we don't mechanically do it. But you have the computer programmer. I thought you were sneezing. I was like, that's a weird sounding sneeze. The computer programmer has to know the math, right? And then make the computer do that math. So you have to have the theoretical understanding. That's why when you get to like high levels, computer science majors and math majors are essentially the same people. I mean, they really are. They're all logic driven. It's all about algorithms and... Okay, shut up, Robert. Let's just keep going here. Y'all read that? A conical cup is 4 inches tall, 6 inches wide at the top. Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. How fast is the water level rising when the water is 1 inch from the top of the cup? So I'm thinking, I don't know, when I was a kid, we had these when I played sports, they had these big old containers or water jugs, and you'd have these little paper cone cups. Yeah, they still have those. So we have a conical cup like this, right? We know that the cup is 4 inches tall. That's not going to change, right? The cup is 4 inches tall. I'll put the little inches symbol on this one. And it's 6 inches wide at the top. So it's not drawn to scale. Again, I apologize. 6 inches across. That's not going to change, right? The cup's not changing shape. Water's being poured into this cup, right? The rate at which that water is being poured in is constant. So I'm pouring water in at, and that rate is always the same. I want to know how fast the water level is rising when the water is 1 inch from the top. So let me draw the water in that cup 1 inch from the top. That should be up here somewhere, right? Somewhere around in there, right? So that's 1 inch right there. Right, I got all my water in here. If you want beer, you can put beer. Do whatever you want. That's the instant in time, right? Now, can you all imagine, like, can you visualize like this situation in the real world? You have a cup, you're pouring in at a constant rate, the water is coming up, right? It's going to slow down. That's the thing you have to understand, is that initially the water level comes up fast because your cone, right, there's less volume down there. And so it fills that space up quickly, but as it spreads out, it slows down, yes? And at that particular instant that it's 1 inch from the top, I want to know how fast the water level is coming up. I like to think of these problems like when you, like real world, when you think of like a dam and, you know, floods, and they're like, okay, the water level's coming up, and they're trying to figure out like, shit, we're going to flood, you know, it's going to go over the edge of the dam. They're trying to measure how fast it's coming up at certain points in time. Okay, this is just a basic problem, a cone and pouring water in it, right? Good picture, yeah? Let's do a general picture. Or do you want to do any givens or wants? I mean, you tell me. You guide me here.
Probably givens and ones first.
Given what?
The givens and ones first.
The givens.
I'm saying to do those first rather than.
Oh, do you want to do the given? Yeah, tell me what you want me to write then. What are you given?
The constant rate of the water being poured in.
The water's getting poured in at how fast?
2 pi.
2 pi cubic inches. Cubic inches per second, right? That's the rate of change in something with respect to time. What is it? Volume of the water, right? The volume of the water. I'm going to put it in blue because it's the volume of the water is changing that fast, right? The volume of the water. I can't label volume on this picture because volume's not a length, right? Volume is the space that's being taken up there. But I can definitely start talking about volume. I know how fast that's changing right now, right? It's increasing. All right. What do you want? You want to know what's speed of what though? The water level coming up? We should draw a picture. Because we need to label that on our picture, the water level. We need to label it. And so that needs to be in this picture, yeah? Okay, so let's draw a general picture. I'll make my cone a little bit bigger just so we can see the pieces of it. Okay, here's my cone. This is 4. This is 6. That doesn't change. Now my water level in here that I'm about to put in here is arbitrary, all right? It's not 1 inch from the top. It's just somewhere in there. So here's my water level. Okay, and I want to know how fast that water level is coming up, right? How fast is it coming up from relative to the bottom of the cone. So I'm going to measure the distance from here to here, and I'm going to call that, I'm going to choose it. I'm going to call it h, little h. That's the height of the water, all right? The height of the water level is little h. And I would like to know then how fast h is changing with respect to time, right? That's what I want to know. Tell me how fast h is growing. At exactly the moment that what? At the moment that we're 1 inch from the top, which means that the height of the water is actually 3, right? You have to kind of deconstruct that in your mind. 4 inches here, 1 inch from the top means the water, the depth of the water is actually 3 inches. So we want this at the moment that h is 3 inches. Good? I'm going to change my h to a blue h because we're talking about the height of the water, right? We're not talking about the height of the cone. The cone is just the vessel the water is in, right? The height of the water is different than the height of the cone. The volume of the water is different than the volume of the cone, right? What now? Equation, right? We need the equation that connects what together? Volume of the cup, volume of the water to the height of the water. So we need some formula that connects the volume of the water to the height of the water. But the water itself is a cone, right? It's a small cone within the big cone, right? It's a smaller cone. So we need to look at our formula sheets for the volume of a cone. So you'll find it in there. They'll draw something like this. It's a right circular cone. They say if this is h and this distance from here to here is r, that the volume is what? 1/3 pi r squared times h. That's the formula for the volume of a cone. You'd look that up, yes?
Well, I thought it was the cube, but whatever.
Yeah, that's the formula. It's actually kind of cool because if you have a cylinder, a right cylinder, the volume of that is just pi r squared times h. So pi r squared, this is h. This is r. Think about pi r squared is the area of a circle, right? Pi r squared. So you're taking the area of that circle and you're multiplying it times h, which is like the depth of the cylinder, and that gives you the volume it takes up. Here, it's almost like, imagine there's a cylinder around this, like this. That's the volume of a cylinder. Exactly, we shed off 2/3 of it. It's at exactly 1/3 of what it would have been had it been a full cylinder. It's kind of cool. Cal 2, we prove this. We can prove this formula easily. I'm actually going to do that next week. So, in my Cal 2 class. So this formula is easy to verify. Okay, yeah? What am I doing? I'm lost. Oh, this is the volume, right? This is the volume. I don't want to confuse it with this one. Okay. This is the volume formula for the volume of a cone. We need to connect V and H together. Is that formula going to connect V and H together?
Yes.
Yes, but there's a problem. What's the problem?
We don't have your dimensions.
You don't know
R.
You don't know R, right? You don't know R. No, it's not that you don't know R. Like when the water is 1 inch from the top, you do know R, right? You could go figure it out. But what don't you know about R?
How quickly it's changing.
How fast it's changing, right? Like we know how fast the volume's changing. We want to know how fast the height's changing, but nowhere in here are we given any information about how fast the radius is changing. If they would have told us, oh, the volume changes at this rate and the radius changes at this rate, then we'd be ready to use the formula. But because there's this R in here, this screws everything up for us. Do you understand that? Like the V is good, the H is good, but the R is a problem. Yeah? You have to imagine what would happen if you differentiate that right now. That somewhere in there you get a dr dt, and you don't know anything about that. Yes?
Can we try solving for R and then taking the derivative?
Solve for R? What do you mean solve for R? Like just get R by itself?
Yes, R by itself and then take the derivative.
You would still have dr dt on one side though, right? Even if you got R by itself here, when you took the derivative of R, you'd have dr dt. So instead of solving for R, what we're going to try and do is eliminate R from the equation. We're going to try and get the R out of here. Now we can't just get rid of it, right? What we have to do is come back to the actual problem, to the picture, the general picture, not this. We have to look at this and we have to analyze, is there anything we can do to eliminate R from the picture? So where is R in our picture? It's the radius of the water, right? So R is actually the distance from here to here, right?